Okay, thank you all for coming so late in the afternoon. I hope you still have some energy. I'm Till, and it's today about the existential theory of the reals. You may not have heard about it, but no worries, I'll lead you to it. Aha. Okay. Okay, so this is a garden of a friend of mine in Amsterdam, and this picture was taken last Sunday. And this friend, she put up these, how they're called, nesting boxes. Who of you has a garden? Not that many, not that many. Okay, so maybe you can't relate to this. Who of you has been in a garden? Okay, you know what a garden looks like. You know what nesting boxes are? Okay, very good. So she hoped for some birds coming into the garden, but that didn't happen. Do you know possibly a reason why the birds didn't come? Actually, a common problem in the Netherlands, that's true. But probably because these nesting boxes could see each other. So a lot of birds, what they don't like is they don't like other birds. They are solitary creatures. And so if you have two nesting boxes and they see each other, none of them will be occupied, and then it's a bit of a waste. So I want to introduce to you the nesting bird box problem, where you have given the layout of a garden, and then you place these nesting bird boxes, which we model as points, and then you can't place another nesting bird box in that region. And then you try to place as many of them as you can, such that you maximize the number of birds in your garden. Is this problem definition understood? Okay, and here I don't know what the optimal number is, but we will, along this problem, I will explain you lots of things about the existential theory of the reals. And the guiding question that we have is this problem contained in NP, yes or no? And yes.
I think this was something similar, but in the opposite.
Yes. We will come to that. Yes, very good, very good. Fabrizio is already thinking ahead. So it's actually an open problem whether this the nesting bird box problem is in NP. It's an open question. Maybe one of you will solve it and then write me an email in a few months. I'm happy to receive these emails. And so let me tell you, so some of you may think I just put a dense grid, and maybe I can show that it's sufficient to put these boxes onto this dense grid. But then you would need to show a lower bound on how dense this grid is, and then you need to check that no two of these boxes of your solution see each other, and that can be done easily. Okay, so there could be this possibility that this problem is not in NP, and then it might be more difficult than NP, and it could be ER-complete. And now I want to introduce to you first with a definition of what this ER is. So you all know satisfiability, where we are looking for variables. Does this work? Oh yeah, variables 0, 1 satisfying some Boolean constraints. And there is this analog problem called ETR, which again stands for existential theory of the reals, where we have, instead of binary variables, we are allowed to use real variables, or we're looking for real variables, satisfying something more difficult. So what we do is, going from such to ETR, is we replace Boolean variables by real variables, and we replace Boolean logic by allowing inequalities and multiplication and addition. And while NP is defined by such, this complexity class ER there, this works surprisingly well, is then defined by this other ETR. Is this definition clear? Okay. So now you know what this complexity class is, and you know what the defining problem is. And because I like definitions, let me give you another definition. So a way to show NP membership is to say we have a binary input, a binary witness, and then we have a verification algorithm that we run on the real RAM. And another way to explain this existential theory of the reals is that you just replace a few of these binaries by real. So instead of a binary witness, we would have a real witness. And instead of doing computation on the word RAM, so that's a normal model of computation, we're doing it on the real RAM. And here it's easy to see that the nesting bird box problem is contained in ER, because you would just describe the positions as real numbers, and then you can do these checking on the real RAM. Okay, and of course, these two definitions that I showed you are equivalent. Okay, so let me show you a few things about birds. So Mikkel pointed out to me that I should call it the fit nesting bird box problem, because sparrows, they like each other. They are happy to hang out with others, but robins apparently not. I'm not an expert on birds, but so it's not with all birds. So what we do know about the complexity class ER is that it contains NP basically by definition, and that it is contained in P space, which is a difficult result by Kenny. And the question is then, where does this nesting bird box problem lie? And I want to go through a few examples of problems that we know to be ER complete, and along going through them, I thought that maybe I can point out also a few things that are maybe different to NP. One of the easiest problem or the most fundamental problem is maybe feasibility. Here you've given a polynomial and you want to find the solution. And here the polynomial is in several variables, has integer coefficients. And already with degree 4, you can have you have the full difficulty, right? So it's a little bit like the 3-SAT version of SAT, one of the base versions. And one thing that you can see here, which are very basic, is if we look at the following system of equations, so we have just x0 is 2 and xk plus 1 is xk squared, then these numbers grows very quickly. So you may have double exponentially large numbers, and what you may have is also you may have algebraic solutions. So
yeah, just a question, please.
yes.
You said one of the ways you framed this different complexity class is you said the witnesses are real and you're talking about real RAM as opposed to word RAM.
Yes.
Can you explain to people that are more familiar with the discrete side of things, what do you mean by real RAM? What does that mean?
Okay. Thank you for the question. So I take the question on what does the real RAM mean? So usually what you have is oh, I see. Yeah. So usually you have a set of instructions, and then you have a CPU, and then you have memory cells. And these memory cells, they can store bits of size W, and then we just have more memory cells. And these memory cells are crazy because they can store real numbers, but each of them only one real number. And there are a lot of subtleties about this definition. There are several definitions out there in the literature. And if you use the wrong definition, then P equals P space. So you should be watching out for this. But if you're careful, and specifically you don't allow access to the representation of the real numbers, then so far we could not break complexity theory.
Okay. Okay, thank you.
Yeah, okay, the first example is feasibility, and the two properties we get is you may need to work with very large numbers or very small numbers, and the other thing is you may encounter algebraic solutions. Both of these things that you don't really know. And this is kind of easy to see that it happens with feasibility, but it happens also with all the other ER-complete problems, or many of them. The next problem I would like to go to, yeah, I'm not telling yet. So who knows what building that is? As a hint, it's in Amsterdam. Some people were correct. At least one person was correct. I didn't hear everyone, but Rijksmuseum is correct. And I would like to introduce to you the so-called art gallery problem. Some people could say also the train station because the same style, but it's the same architect, but it's a different building. So that's the art gallery problem, which is kind of the inverse of the bird nesting problem. Here you place guards such that they see everything because you have this very expensive paintings in the Rijksmuseum. Many of them Dutch, others just stolen from other countries. I was apparently the British Museum basically doesn't have British art. Well, they didn't steal it from other countries, right? But then this guard here would cover this area and protect the art. And then you want to have now as few as possible guards to see the entire gallery. That problem, I think people have heard more often already. Yeah, and here I want to tell a little bit of a story behind this art gallery problem, which I think also happened in other ER-complete problems. Yeah, so the question is now how precise you need to be. And you already know the answer because I set you up on this. But back then, people didn't know the answer, right? Like 5 years ago, no one knew. And I think this is what happened. And I think this is also what happened to me, is if you're a student, you're like, oh, it's probably easy. I shouldn't ask my supervisor because it's embarrassing if I tell. And the supervisor says, it's probably easy, should give it as an exercise to the student, right? And I'm not entirely, probably never exactly in this way happened, but I can imagine this happening a lot because what happened is that people did not really speak about this. So I give you some examples. So Lee and Lin, they were one of the first people talking about the art gallery problem. They showed NP hardness and they said, oh, we think you can just place the guards on the vertices. And that's wrong because if you look at this gallery, then the optimal solution, you need one guard that sees everything. And if you place your guards on the vertices, you need at least two. So they overlooked this, but they thought, oh yeah, maybe we just need this. And then Joseph Oroku, he said, usually showing NP membership is easy, but here we don't know, so we skip it. And he's a good guy. He talks about it, right? But then a lot of other paper following up on this don't even mention that this is maybe an interesting problem to look at. So usually you always show NP membership, you don't show it, and now you're not talking about it. And then at my age, like, you know, when I started in research, I was thinking it's probably not interesting, no one is talking about it. Yeah, I don't know. I think it's a little bit of something we have to be aware of, that we should address the things that we don't know, even if it's like, you know, we have the theorem, but yeah, it can't do everything, or there we have an embarrassing knowledge gap. And maybe it's not so embarrassing after all, because you're all smart people. If you haven't figured it out, it's maybe not that easy. Yeah, and then the story continued. We somehow started looking into this, and then we found that irrational numbers could be possible. And so this will be the only proof in the entire lecture. So bear with me. So this polygon here, it has all rational coordinates, and it has here these hooks. You see those? And what happens is here you need to see you need to be on the line as a guard in order to see those two hooks at the same time, because one is on the right of and the other is on the left. Does that make sense? And then I have this construction 2 more times, and then we have 3 of those lines, and then you do need to have one guard on each of those lines in order to see at least these hooks. And then what you can see between kind of intuitive, that if you want to see this pocket here, okay, it's not working as great as I thought. I have to get used to it. Those 2 pockets, then basically as the first one is on this line, the second one needs to be on the left of this red curve, which is maybe something you can imagine, that if I move along a guard along here and move it up and down, that I can trace what is not seen on the top and not seen on the bottom, and then the red curve arises. Do you trust me on this, or? Okay, I have also no backup explanation, to be honest. Yes? Yes, yeah, exactly. So for every guard position here, I get a point on the red line. And it's some quadratic curve that you can compute. And the same argument goes from the right, and then by coincidence, these three lines or three curves intersect in a single point, and that will be the only solution, and that will happen to be an irrational solution. And on hindsight, it was not so hard to find, and it is certainly very easy to show, or minus these ugly calculations, and convince everyone that this is irrational. But for a long time, yeah, this was kind of missed. And somehow it didn't took us much longer afterwards to show the ER-completeness. And that is a very complicated proof. But I think that this was a key step, right? So first realize, oh, this is a problem we should really look into. And these were my co-authors, Mikkel Abrahamsen from Copenhagen and Anna Adamaszek, who's also still in Copenhagen. The next problem I'd like to talk about is packing. You all know packing from daily life. And here I have a unit square container and unit squares that I want to put into. And the objective is here to have the smallest square container as possible. And what happens is that this is the best known solution, but we do not know if it's optimal. And that's another phenomenon for these ER-complete problems, that sometimes, yeah, so we do not know if it's optimal, and that small generic examples can be essentially unsolvable. All right. If now for SAT, if I give you an instance of size 11, you can brute force it, or any most other NP-hard problem, right? But here, I just take a very simple generated problem. But it also is problem dependent. So for the art gallery problem, it's much harder to define difficult problems. Yeah. And then we also showed that this problem is complete, and this then we replaced Anna by Nadia, who's in Berlin. Okay, the next problem I'd like to show you is training neural networks, and this I mainly want to show you to show you the scope of things. So because I felt that at the beginning people said, oh, these ER-completeness, it seems to be like a geometric thing, but I think it interleaves in lots of different areas. And here I would like to start with the definition of what a neural network is. So you have some input, it's basically a function. You have some inputs, which could be some numbers, and then this neural network has weights and biases that our task is to choose them in a clever way. And then we do these computations that we multiply these inputs with the weights, and then send them and add them all up, and let's give the activation of this node. And we also add this bias, and then we get the activation. And here in this case, it's -1 for those examples. And then we apply the activation function, which is just like, it just looks like this here as a graph, and it's just max of A and 0, of the activation 0. There could be other activation functions, but that's the most used one in practice, and also one of the easiest to describe and work with. And then you multiply further, and you get the output. That's a neural network. Sorry. I guess I hope this is clear, the definition, otherwise I couldn't repeat. Okay, if you haven't got this thing that you should remember, we try to find these weights and biases, and we compute some function. So here a neural network, I think of it just as a function f, which is parameterized by some theta. And here I consider the neural network, which is fully connected and has 2 layers. So actually, I mean, it's a graph, right? But really the input is just 3 numbers, the number of input neurons, the number of middle neurons, the number of output neurons. And then the training problem is someone gives me some data and some threshold, and we try to reduce the cost of, like, we want to have this function, this neural network output the same as the label that we are given, and that's the training problem. So we have these data points here, xi, yi, and we plug in xi into this function, and we want to ideally get out yi, and we may not always get it. And then we add up all these costs. Is the problem definition clear? And this is work with my co-author Simon Weber from Zurich, Daniel Bertschlang also from Zurich, Paul Jungenblut from KIT, now I have to think, Karlsruhe, and Christoph Hertrich. I think he is currently in London and will soon start a postdoc in Brussels. Yes, and we showed also that this neural network problem is ER-complete. And here the main message is only not just problems in computational geometry are relevant, but actually in lots of different areas. So maybe the bigger picture is that, yeah, you can look at CSP, you can look at, of course, graph drawing, but also simplicial complexes, matrix factorization, tensor decomposition problems, Nash equilibria. In a lot of areas, wherever you have some real numbers, look out for ER-completeness. Now I would like to give a little bit of an intuition. So you see now a definition, you saw examples, but how should I think about this complexity class ER? When I see a problem, what should give me the intuition that it's ER-complete? And there are 2 factors that give me ER-completeness typically. And this is the solution is continuous and nonlinear. So you can see this for this nesting bird box problem, right? Or the art gallery, where you see this visibility regions, they change continuously, but also nonlinear. So because in the first step, you know, the visibility region changes only a little bit, but then in the second step a lot. And that's the nonlinearity of it. So similarly with packing, I rotate this piece here, and you can see that these distances here are equal, but these distances here are not equal. So you see again a nonlinearity in the behavior. And that's exactly the 2. Then if you see those 2 ingredients, your alarm bells should ring and say, oh, ER, ER. Okay. And another thing for intuition is, so if all of you work on problems that are maybe NP-hard or NP, and if you see a problem, a discrete problem, it's often very intricate of whether this problem is NP-hard or NP. If you see something that smells like ER, it's almost always ER-hard. So it's a little bit boring. It doesn't mean that the proofs are easy, but it seems almost always a story that if you have some ingredients of this ER-hardness, you almost always have ER-hardness. So in a sense, intellectual, yeah, there will not be so many surprises. And this intuition, we could confirm with a set of problems, and namely constraint satisfaction problems. So Marcin gave a very nice introduction in the morning about constraint satisfaction problems. But for those who don't have a memory for what happened in the morning, they will be reminded again. So in constraint satisfaction problem, we have a domain, and we have these constraints, or there should be an end. And we want to satisfy all of these constraints. And what is important is 2 things. So what types of constraints we are allowed to enforce, and what is a domain. So I think tau is called the type. And it can encode lots of different problems. Martin gave a lot of examples. I want to just give a few here. So, for instance, 3-sat you can encode by having a universe being 0, 1, and then the constraints you have are just all of these types of clauses that you can have, negation or not negation. And this gives you a host of different constraint satisfaction problems. And then, yes, and now I can also look at constraint satisfaction problems over continuous domains. So here I just take this interval -1 to 1, and the easiest constraints that I could have is maybe addition, setting a variable to 1, and multiplication. And that constraint satisfaction problem is easily seen to be ER-complete. It would take a little bit long and the technical to show, but it's not difficult, because if you want to simulate a polynomial, you just decompose it into additions and multiplications. And then we could replace this multiplication by something easier, namely squaring. Because you can simulate squaring, you can simulate multiplication using squaring by using, how is it, x plus y divided by 2 squared minus x minus y divided by 2 squared. And this is then like this. Okay, I chose the right vector here. So you see here, I just use squaring and addition and I get multiplication. We can then also replace the squaring by inversion. And what was kind of surprising was that you can replace this nonlinear constraint by anything f that's nonlinear. Okay, I'm a little bit lying here, but essentially this is true. So this kind of the intuition that I told you earlier, that anything that has these two ingredients is ER-complete. For CSPs, we could essentially confirm as long as you have addition and setting some variable to 1. Yeah. So, and we use this result only once for packing, but in theory, you could use this now to as a starting point for further reductions. Okay, that was clear. Yeah, so, and let me repeat. So yeah, for if your domain is finite, then it's an intricate theory of whether you have FPT algorithms or not, and it's really hard. But if your domain is continuous, anything nonlinear goes. This is joint work with Rainier Schmiermann. He didn't find an up-to-date photo, but he finished his master's thesis when he was 19, and unfortunately he's lost to algebraic geometry. But okay, that can happen. Okay, so now to the last part of my talk is the tools. So once you've given an ER-complete problem, what can you do with it? Because we want to also solve problems. And the sad news is that essentially most of these tools that we all usually develop are not working. Or at least I have never really seen them working. And that's a problem. But at least there are some tools that sometimes work, and it's somehow, I think, also a reason why this complexity class is a little bit, it doesn't stimulate so much research if you can't show any algorithm for this. But it may be also that if someone works on what is it, TSP and can solve 100,000 nodes, but then someone works on packing and can't even pack 20 or 11 unit squares properly. It's not that the one is smarter than the other, but it may be also because just one problem is inherently more difficult than the other. But what type of tools are there? So there are symbolic tools. And these symbolic tools, I want to illustrate here, for instance, if you want to find the zero of this polynomial, right? You don't really know maybe how this graph looks like, but you can tell me if this has a 0 or not, right? So who says it has a 0? Anyone volunteer to explain why? Is cross a horizontal line? Why does it cross a horizontal line? By this way, I'm not sure this is a correct graph. Odd degree, very good. So if you go to plus infinity, the function goes to plus infinity. If you go to minus infinity, the function goes to minus infinity. But this is kind of symbolic reasoning, right? We reason without actually plugging in any values. And these methods, they give optimal solutions. They have provable time bounds, and in theory, they're the best you can have. And you can encode NP-hard problems into this, so you cannot actually get better in theory. But it doesn't help because in practice they are horribly inefficient. So I'm not really sure what we can make out of this. They're good to maybe argue about those things, but if you really want to solve something, I think these symbolic methods are not flying. Then we have gradient descent methods. I guess most of you know what gradient descent is. I have a new way to explain it. Okay, you know. And this has kind of the flip side of these things. Namely, it's super efficient in practice for a lot of problems, but it basically comes without guarantees. And sometimes people tell you, oh, but we have now this theorem which shows that if you run it forever, at some point it will end up in the solution. But this is really something extremely weak, because if a monkey types all possible solutions in a typewriter, at some point he will or she will also type the right solution. So the guarantees of gradient descent are typically very, very low. And then there's discretization, which in some cases works. And so it has both provable guarantees as well as this efficiency in practice. It's not as good as gradient descent often, and it doesn't have so strong guarantees, but using additional assumptions does sometimes work. And I would like to showcase 2 examples on how these additional assumptions could work. But notice we also kind of we're in desperate need of these additional assumptions, which we try not to do, but I think it's justified to try them. And the first of them is smoothed analysis. Who in this room knows what smoothed analysis is? A third or something. Okay. Okay, I have a little bit of time, so maybe I can explain smoothed analysis. So smoothed analysis is we have average case complexity where we take a random instance, which is very good for us because random instances have a lot of structure and they all kind of look the same. And we just try to analyze this random instance. Or what we can do instead is we analyze worst case instances. Maybe I should support this. And here everything is random, and here nothing is random. You just look at the worst thing. And smoothed analysis, it tries to interpolate between those two, where say we take the worst instance but perturb it only a little bit. And that's why it's called smoothed analysis. I think it's a misnomer because so many things are smooth, but that's the background of it. But using smoothed analysis, we could show that a fine grid will contain the optimal solution. So we basically take a worst case polygon, perturb it a little bit, and then we know that the solution will be on the fine grid. Is this something that our birds will be happy with? I mean, it shows kind of an NP membership oracle. Okay, I already showed the bird being said. But I think the bird shouldn't be happy with this result, because you still cannot like use this result to actually design an algorithm that is actually practical. This work with Jeff Erickson and Ivo van der Hoog. This is the enemy of all birds. Okay. So another approach would be to use some assumptions that are more problem specific. And one thing that's easy to observe here is if you look at, let's say, this nesting bird box problem, if you have two boxes placed very close to each other, but they are close to a reflex vertex, so this vertex here is called the reflex vertex, then the visibility region changes a lot, right? That's easy to see. But here around that reflex vertex, that's far away, visibility doesn't change basically at all. It's kind of irrelevant. So, and that's clear, right? Yes, no? Okay. Can you see this? Oh, there you can see it. Okay. So the idea would be to say, okay, let's maybe place more candidates close to these reflex vertices and fewer farther away. Because if you're far away from all reflex vertices, they're all kind of having the same visibility region, so they may be behaving all similarly. And easy way to do that is to shoot rays from every reflex vertex and take all of those intersections. Now this picture looks really messy, but from a theoretical perspective, the number of intersection points are not so big. And now that's a nice, let's say, approach. But the good thing about it is we can also prove under specific assumptions that this approach will lead to a good solution. And what are those assumptions? So you can look at visibility regions. So you see here this guard or bird box. Let's stay with the boxes. This bird box here, it has this visibility region in blue. And we can think about that we enhance the visibility region of this. So for instance, you could say maybe a bird box doesn't just want to see another bird, but it also doesn't want to see slightly around the corner another bird, right? Or we could decrease it. We could say, well, okay, this little region here, it doesn't affect us by too much. So depending on how we define our visibility region, the larger these visibility regions are, the worse our solutions get. Yes, so because, yeah, so the larger the visibility regions, the more we forbid. But the number of boxes that we can place is discrete. This means we will have the same cardinality and then we do a jump, and then we have the same cardinality and then we do a jump. And the question is, where would this jump occur? If this jump occurs at 0, we have a problem. But the question is, why should the jump occur at 0? And our assumption is just that these jumps will not occur at 0. So using these ideas, yeah, that's maybe a sketch here. But yeah, I hope to convince you that this assumption is justified. And in practice, it really seems very rarely that the jump here appears at 0, because that would mean we also get some rigid configurations where the positions are fixed. For the art gallery problem, we then also implemented it, and we were competitive also with other practical algorithms, although not as good as they were. But yeah, I hope to make the birds happy with this. And this was joint work with Simon Hengelfeld, my master student back in the day. A last remark is that actually the name of the problem came from Mikkel Abrahamsen, and these are the nesting bird boxes that he put into his garden that he asked me to show you as well. And oh yeah, so I would like to say a few open problems. So maybe if you work in some area and you all work in different areas and you keep your eyes and ears open, maybe you find also some problems that could be ER complete. Don't be afraid of them. I would like to find appropriate assumptions also for other ER complete problems and see if we can solve them. For the art gallery, there was an example, but maybe there for other problems we can also find appropriate assumptions. And yeah, in general, it would be nice to develop tools that are provably, that we can prove something about for these ER-complete problems. And with this, I would like to thank you for your attention.
We have some time for questions. You, yeah.
Thanks for the talk. So, what's the status of the art gallery problem in the polygon with holes? Like,
Say again?
so if there is a polygon with holes,
Yes.
so what's the status of that? Is it ER complete or like
Which problem?
the art gallery problem?
It's already ER complete for polygons without holes.
And let's say there is, and let's say if one only look after the boundaries of the polygon.
Say again?
So if one is to look only at the boundaries of the polygon, no need to like worry about the inside of the polygon. Is it ER complete again or like?
Yeah, so Jack Stade has some update. And so if you can place your guards in the inside, but you have to guard the boundary, then it's still ER complete. So that's what he showed. And whether when your guards are on the boundary and you want to guard the boundary, then he thinks that should be in NP, but I think it would be difficult to show it, but it would be interesting. But that's an open problem.
Thank you.
So some other question? Yeah, one there.
So you said that usually when you think a problem is going to be ER complete, it is, but have you ever come across a surprising example when you thought it was and then it wasn't?
Did I come across some surprising example? Yeah, recently we came across with Linda Kleist some very surprising example. Yes, so sometimes, yes. So we looked at this so-called epsilon Rudy problem, where you want to represent graphs. So where you draw an edge whenever the distance is at most 1. And you don't draw an edge if the distance is a larger one. And what we did is we said, okay, we know that this problem is already ER complete to recognize these graphs. So the input is such a graph. And the question is representable. And we added here such an epsilon. So far, so good. And the epsilon is part of the problem description. So now what I did is I defined for every number between 0 and 1, I defined an algorithmic problem. And we found dense NP thank you. Dense NP witnesses. So wherever you are here, somewhere densely, somewhere very close, arbitrarily around you, pick some epsilon, And you will have a version of this problem for which we know there always exists a witness for NP membership. We don't have NP membership, but a witness. At the same time, we have this sequence converging to 0 where we know ER-hardness, where it really blurs with what it means. But that would be one of the confusing examples. That was very much surprising us. And we want to show at least for one example that we have NP membership, but we cannot at the moment. Thank you for the question.
Okay, another question.
So does the sum of square roots problem fit into the framework?
No. So let me mention the sum of square roots problem. So you have numbers. So you have this A1 plus A2 minus A3 and so on. And you just want to decide if it's larger to 0 or not. And we do not know if this problem is polynomial time solvable, and we do not know if this problem is in NP. This is a big open question for a long time. But it seems that this problem is easier than ER. From a practical point of view, and we do not know any examples where you would need to use high precision. So in practice, people just compute this for not so high precision, and they can decide this problem. There are no examples known for which you would need high precision. So it seems everything points toward that it is polynomial time solvable, but we do not know. So it is within the realm of things that are outside NP, but it seems not to be ER complete. For all that we know for now. And maybe an embarrassing example is, so given a bunch of points in the plane, we can compute in polynomial time the minimum spanning tree, but we cannot determine its length. Because we can't solve the sum of square root problem.
Other questions? Okay, over there.
So now that you have like a theory where you can also talk about real numbers, are there even further extension of those where you can maybe talk about something like subsets of real numbers, where then the domain would be something like the power set of the real numbers, or then going up to lengths of higher cardinality even?
Okay, further extensions. So people do look into this. What I can say to this is you need to be very careful with those. So if you have sine function and pi, just those two things that you add to your vocabulary, then suddenly you become undecidable. So there was a recent paper, for instance, that said we have also, we look at neural networks with different activation functions like the sigmoid function, and then they can show completeness for these extended vocabularies. But I think very quickly you come into the realm of being undecidable. I also don't really know where subsets of real numbers would be. I mean, how do you even describe them? If they're intervals, you just describe the endpoints. So basically you only have real numbers. True that, yeah. So I don't know of examples where this would be relevant.
Okay. So I don't see other questions. Then let's thank again the speaker for this very nice
Thank you for attention.